Today I will present one or two Oblivious transfer algorithms. Rhythm is here is the name of this algorithm. Suppose we have two parties, Alice and Bob, and first Alice has two messages. It's at M0 and M1, and B want to choose one messages. And the goal is that Bob can choose one of the messages. For example, he choose maybe B is 1, 0 or 1. He will choose MB, but he do not want Alice to know anything about which message he choose. That's the goal of this algorithm. Any idea about
You mean Bob? You mean Alice do not know Bob to which message?
Bob choose one message, but not Alice know anything which he choose. And this is part of an algorithm I use in the summer. Part used to part algorithm of double circuit I will present before. Part of the protocol. And I want to more concentrate. I want to say that this model is called Alice is a semi-honest model, which means that under all the protocol, Alice and Bob will follow the protocol, but they are smart enough. They can influence the others. They have curiosity to influence the others' message. But under this protocol, under this algorithm, we can guarantee that both cannot learn others' message and they just follow the protocols and will not change the protocol. And before I talk about the one or two Oblivious transfer algorithms, I will first this protocol is based on RSA encryption. I will first to introduce RSA encryption algorithms. And RSA is a public encryption algorithm. Public key, which means for a part, it has an encryption system, which means an encryption system and encryption systems. The part will publish the encryption parameter to others, and others can use the encryption parameter to encryption their message, and then send to this part, this part, and which is I will use the lowercase. Suppose we have n parts in the upper, and they can use the parameters encrypt message, but if they do not have the encryption parameter, there is no way they can other people can encrypt the message. That's what it means public key encryption. And for this, they have two parameters. One is encryption, one is decryption. And for this part, it will keep secret the decryption parameters for other people to know to decrypt the message and publish the encryption parameter to others. so other part can decrypt their message and then send to the central part. And the central part can use the decrypt parameter to decrypt the ciphertext and then get the real message. But for other part, even they get this method and do not have decrypt parameter, they cannot learn anything about the plain text. That's the public key encryption algorithms. In the following, I will talk about RSA systems. For RSA is suppose a condition is that for this reception and suppose PQ are two big params, and if we multiple them together and then send to others, and it's hard to factorize this big integers. This is the assumption of RSA. And in mathematics, it's easier to test if the number is params, but it's much harder to factorize big integer. And it has the fast algorithm such as Robin-Miller test can test if a parameter is if a big integer is prime or not. And based on the assumption, we can first to get two parameters PQ which are bigger primes, and then I will from the central part, for example Alice, it will first to get two big primes P and Q, and then they can go Euler torsion function of n, which is equal P. The Euler torsion function means that for all the integers, and if we modulate in n, and we can divide it in n classes, and this number is equal to the co-primes to n, which means co-prime means for two integers, their greatest common divisor is equal to 1. This is co-prime means. And for n, there are so many numbers that co-prime with n under the n under this modular. It's easy to test. So based on this formula, we have an Euler formula, which means that which is A is a co-prime with n, and this is the Euler torsion of n, and then the square of A, the power, the polar n power of A is equal to 1. And just to remember this conclusion, and also this is easy to prove, and if you have interest, I can show you. We do not have to skip, just remember this conclusion, and RSA is based on this conclusion. Okay. So for Alice, we will get two big parameters, PQ, and then we get N is equal to PQ, and phi N equal to P minus 1, Q minus 1. Then Alice will publish the parameters of, okay, he will choose, and he will then choose D, which is co-primed with phi N, which means equal to 1, and then he will, she will get, based on D and phi N, he can get parameters, to get a parameter E. Based on this E can be found by Oakley extended algorithms to get this E, which is ED is equal to K phi N minus 1. K is the sum of integers. And based on the algorithm, so we can get the D. And then he has parameters N, E, D, and will publish N and E outside. Suppose Bob here, we get the N and E, and Bob has his message M. Then he will encrypt this message by this form. For the N, and get several types of C, and then send the C back to Alice. When Alice gets the several test, he can use parameter of D to get M. I will show you here. When he gets the C, when Alice gets the C, he will calculate the power of D to D, which is equal to M D D. C is equal to this one, and which is equal to M E D, and how E D is equal to cofine this one. Phi N minus 1, and this can transform this one from the Euler forms. If A is a co-prime with N, then because message our real presumption is that M is a co-prime with N. Because if you find some message that is not co-prime with N, then you will break this system. So this is equal to 1 from Euler formula, and then equal to 1 M, which is equal to M. Alice gets the plain text M. That's the whole of our RSA system. It's based on the Euler formula. And now I will use the RSA to talk about the one or two Oblivious transfer algorithm. This is the at first, Alice have two messages, and Alice will generate RSA systems, which is N, D, E. Then and also he will generate two random numbers, x0 and x1, and send some parameter to Bob. The first parameter is the RSA system, the public system, to Bob, and also he will send Bob the two random numbers, which he generated, not the message, the two random numbers to Bob. Then Bob have B with ground 0, 1. He will choose one of one data from x0 and 1, if which is xb, and then discuss another number and discard x1 minus b. This is discuss, and he will encrypt data and in the following forms. General way of K is a random number generated by Bob. He just generates random number and encrypts this number and plus XP. Then Bob will send back the V to Alice, and Alice will get the following forms. For this case, Bob will keep it secret. He will not let Alice know anything about the key. So when he sent back, Alice do not know anything about it. V is belong this plus xv and x1 are also do not the key. He will minus x0 off and also minus x1 and then decrypt this data. And I will show you example. If Bob selects x1, then v is equal to minus x1, and when v is minus x0, which is equal to this k0 is equal to for example, if Bob choose x1, then v is equal to this forms, and k0 is equal to this one, which is a random numbers. And when he choose x1, then k1 will minus x1, and then use RSA and optics. This is equal to E and decryption, which is equal to K. So, but Alice does not know anything about K. So both number K1, K0 is a random number for Alice. And then Alice will design another two number M0 and M1, which which is equal to M0 plus K0 and M1. M0 prime equals to M0 plus K0 and M1 prime equal to M1 plus K, and then set these two data back to Bob. And because Bob knows which data he chooses, the order he chooses, he will minus and he knows K. Then he will just to minus this K to get the message which Bob will choose and discuss another message. And so by this all the protocols, Bob will select the MB, but Alice do not which one he choose. That's the protocol of Oblivious encryptions. This is the final result Bob get. And Alice do not know anything for this RSA protocol.
What is MP?
MP means Alice have two methods, M0 and M1. Bob will choose one. Bob will have the choose can be expressed as B0 or 1. So we will choose MB. Okay. The goal is Bob want to get SP and do not want to Alice know nothing about B. And finally, under RSA, can achieve this goal.
In the final step, is sending both M0 pi and M1 pi back.
Yeah.
Alice is sending both M0 pi and M1 pi to.
Oh, these two data sent back.
Oh, okay.
Yeah, because one is random numbers. Even Bob get it, it does nothing.
Okay. So you mean for K0, for example, your example is like Bob choose B equal to 1. Is that like let's say Bob equal to 1? Then for K0, like Bob is not able to know what is K0. Yeah, K0 I mean.
K0. Yeah. When this is V minus X0, then the power of D. This is random numbers because this is supposed not equal, and Bob do not care, and then use the encryption method. And this parameter, even if you give this parameter to Alice, it will do anything.
But Bob know X1, X0, right?
Yeah, the Bob knows that by the 0.
He also know D, right?
D. Bob do not know D.
Okay, Bob, you know, okay.
Just because D is
Okay.
As a matter of fact, I think these steps have the function of signature here.
What do you mean, like?
Because let me check things. This one. privacy is wrong. Because as a matter of fact, if you send this data can be decrypted by Bob because it can K0 power E and then it return number. So it's not signature.
Yeah.
Not
You
signature.
should not be able to.
Yeah, I will tell you, but this is any question. But I think this steps is very smart here. For the symmetry encryption algorithm cannot achieve this goal.
Say that again.
This is asymmetry public systems, but I think for the symmetry, for example, use the public key and
Symmetric key, you mean?
Symmetric encryption systems. The Bob will decrypt some of the data. So just in the encryption, this asymmetry to protect the privacy for one.